Hi, I'm Jonathan Aldrich. Today, let's put on our architecture hats and talk about data representation. Data represented in memory is untyped. It's just bits. So when we operate on that data, we have to specify the type as part of the operation. For example, a signed shift and an unsigned shift might be different. When we store integers, they come in different lengths. Typically, they come in half-word, word, and double-word lengths. Sometimes integers can be stored in bytes too. For example, SIMD instructions that you might find in MMX extensions to the x86 or in tensor processing units or TPUs might operate on many bytes at a time. Floating point numbers come in both word and double word lengths. We call these single precision and double precision floating point numbers. And those are typically 32-bit and 64-bit precision. So this is in a world where word is 32 bits. There are two ways that we can store integers, little-endian and big-endian. And it affects the way the bytes are laid out within a word. So in a little-endian representation, the low-order byte is the address of the data. So if we have a piece of data at address 16, then the low-order byte will be at address 16. And then address 17 will be the next byte, address 18 will be the next byte, address 19 will be the last of the 4 bytes. This works well if we access the same memory with different size of numbers. So if we write a word that holds the number 37, if we then later read a byte, we'll get 37 because we're reading that low-order byte of the word. On the other hand, big-endian is a different organization. The higher order byte is at the address of the data, and then we go to lower order bytes. So this is more intuitive in the sense of how we write down numbers, right? We typically write numbers with a high order byte first, and so this lays them out in memory in the same way. The x86 platform happens to be little-endian, and so as that's dominant in desktop machines, that's a common format to access. On other common processors, you can actually configure whether data is stored in a big-endian or a little-endian way. Let's look at little-endian versus big-endian in a more graphical way. At the very top, we can see how data might be stored in a big-endian format. So if we have the number 37 and we store it at address 432 as a word, then the bytes will be 0, 0, 0, and 37 because the low order data 37 will be in the last of the 4 bytes. That's just how we write down the number in decimal. On the other hand, if we have 12, 34, 56, and 78 as our 4 bytes, and these are hex numbers, we'll talk about hex in the next slide, then they'll be laid out again 1, 2, 3, 4, 5, 56, 78 in the bytes. Little-endian, on the other hand, reverses this. So the first word is still first, it's at location 432, but now the low order byte, the one that holds 37, is first. And then at address 436, if we write 12, 34, 56, 78 in hex, then the 78 comes first, followed by 56, 34, and 12. We can also think about this in the second lower part of this diagram, visualizing memory as a byte addressable array of words. So here, again, 432 address will have 00037 in big-endian notation. And we read the bytes in kind of the usual way, right? Increasing addresses going left to right, and then we go down to the next line, left to right, and so on. On the other hand, little-endian, it reverses the addresses. So I've actually drawn this with increasing addresses going from right to left, right? 432 to 435, 37, 0, 0, 0, 78, 56, 34, 12. The increasing bytes go to the left, but we can read it to the right in the normal way. It tells you about how little-endian is basically storing it in the opposite way from how we read it. Let's talk about integer arithmetic. Integers are represented as binary numbers. And for unsigned numbers, we just use binary place value. So the range is 0 to 2 to the n minus 1, and the low order bit tells us, is this even or odd? And then each bit going up tells us whether 2 to that bit's place is present in the number. For signed numbers, we use something called 2's complement. And so the total range is 2 to the n, but the actual numbers will range from negative 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. That minus 1 at the end is because, of course, we have to represent 0, and so we can't represent the same magnitude in both directions. Writing bit patterns can be awkward and long, right? Lots and lots of ones and zeros. So when we talk about binary numbers, we often represent them using hexadecimal digits, or base 16. And in figure 5.3 here on the right, from the textbook, you can see how these are represented. So 0 would be 4 zeros, 1 would be 3 zeros followed by a 1, and so on with binary notation. Once we get to 10, the number 10, we're going to use A for that, and then B for 11, C for 12, D for 13, E for 14, and F is 15. That's 1111 in binary. So that way, OX, we write binary numbers with OX in most programming languages. So OX ABCD means the hexadecimal number ABCD, and we can just read those off the table. So that would be A would be 1010, B would be 1011, etc. So this number is actually 43981, but you can see the pattern of correspondence between bits and the number better if you look at hexadecimal, right? Because you can break it down 4 bits at a time, base 16, and the correspondence between the bits and the numbers is more clear than if we use base 10. When we do arithmetic, we use a representation called 2's complement to make things work better. So if you think about how to represent negative numbers, a very obvious approach might be to have a sign bit, which might be in the higher order, the highest bit by convention, and then use the rest of the bits for the magnitude, right? So to represent the numbers 1 through 8, we might have, or 1 through 7, we might have 0 through 111, and then we might have negative, the negative numbers be -1, so 1 and then 0, 0, 1 for the magnitude. But most processors do not choose this because it requires different algorithms for subtraction and addition. And it turns out with a trick we can combine those, and so we can use the same algorithm for addition and subtraction. 2's complement is the representation that allows us to do this. The intuition here is that we can basically represent numbers if we represent numbers in an unsigned way with n digits, then when we do addition on them, it's actually addition modulo 2 to the n, because as soon as we get to 2 to the n, the carry bit drops off the end and we just wrap around. So that works for 0 to 2 to the n, or -1, but we can actually pick any range of size 2 to the n. So what if we pick the range -2 to the n minus 1 to 2 to the n minus 1 minus 1? Okay, so if we have, for example, 4-bit numbers, then that would represent -8 through 7, right? -8 is -2 to the 3, and 7 is 2 to the 3, or 8 minus 1. So the lowest number is represented as a 1 followed by all zeros. So -8 is 1, 0, 0, 0, and then we just count up. So -7 would be -8 plus 1, right? So we get 1, 0, 0, 1. -6 would be -8 plus 2, right? So it would be 1, 0, 1, 1, 0, and so on. What's nice about this is because we've organized the numbers so that they're in order of their magnitude, then when we do addition modulo 2, we can add negative numbers to positive numbers, and it just works. So in this representation, there are some nice properties, right? The most significant bit is the sign. So we have the most significant bit is 0 for all the positive numbers, including 0. And the most significant bit is 1 for all the negative numbers, including -8 here in this example. And the non-negative numbers are represented exactly as unsigned numbers, right? So 7 unsigned is 0, 1, 1, 1. And we've represented it here signed in a signed way exactly the same, with the same bits. This allows us to convert between signed and unsigned numbers very easily, as long as the unsigned numbers are within the range that could be represented by signed numbers. So between those advantages and the ability to use the same algorithm for addition and subtraction, 2's complement is a very nice representation for hardware. How do we represent floating point numbers? Well, there's a standard that's used by all practical processors these days. It's called IEEE 754. And there are 2 different lengths of floating point numbers that it specifies. 32-bit precision, which is called single precision, and 64-bit, which is called double precision. In both of these, the first bit is the sign bit. So that'll be 1 for negative numbers and 0 for positive numbers. We then represent the floating point number with a combination of a mantissa and an exponent. So the exponent comes first, and basically we're going to say that the exponent represents 2 to some power, right? So if the exponent is 10, that'll be 2 to the 10. And so this allows us to represent very large numbers with floating point numbers. In general, a number that we're going to represent is of the following form, shown here in the value. So it's going to be a number 1 point something, which is represented by f, the mantissa, times 2 to the exponent. But we're going to offset the exponent by a bias. And so that bias allows us to represent negative exponents, which will allow us to represent very, very small numbers, right? 10 to the 2 to the negative 15, for example, right? So the exponent that we actually use is going to be the number stored in this field E, which will be 8 bits for single precision and 11 bits for double precision. And then we're going to subtract the bias from it. So 8 bits will represent 1 through 256. So the bias will be 127, allowing us to use half of that for positive powers of 2 and half of that range of the exponent for negative powers of 2. So the exponent for single precision will be e minus 127. And for double precision, it'll be e minus 1023. So because our floating point numbers are of the form plus or minus 1 point something times 2 to whatever power, we don't have to represent the 1 explicitly. And so the f is everything that comes after the 1. It's everything that comes after the decimal. So there'll be 23 bits of mantissa in single precision floating point numbers and 52 bits of precision for the mantissa in double precision floating point numbers. So field f is called a fractional point, and we compute based on that. There are some special patterns that are used. So naturally, 0 will be with an exponent of 0, a mantissa of 0, and we get the value 0. It turns out floating point numbers can represent plus or minus 0, which is useful for consistency of arithmetic with floating point numbers. We can also represent infinity. This is used when the exponent is twice the bias plus 1. So the bias is 127. So twice the bias plus 1 will be 255. That's the highest possible number. That will be a number that we can't use this exponent to represent an actual number, as we reserve it for plus or minus infinity. Our normal numbers are for exponents between 1 and 2b. If we have an exponent of 0, then we're going to be representing a number that's 0.f times 2 to the 1 minus the bias. So implicitly, the exponent is treated as if it's 1. We subtract the bias as usual, and this is for representing very small numbers. So they're smaller than the smallest number we could represent in the normal range of floating point numbers, where we always start with 1 times 2 to the e minus bias. But we can use a fractional floating point number by just using 0 point whatever the f is. And so we can sort of gradually represent numbers that are increasingly close to 0 at the smallest end of floating point arithmetic. We can also represent Nada numbers as situations where we have that maximum exponent e to be plus 1 with a non-zero fractional part. Let's check our understanding.